Welcome to the Learn Efficient Light Pipe Design using virtual prototyping. Thank you all for taking the time to watch this. And our agenda today is efficient light pipe design. So the first thing we want to start looking at when we start talking about light pipe design is what is the goal of the design? And we want to be able to specify, is it efficiency? Is it total output? Is it uniformity? What are we trying to do and what is the goal? The next thing we're going to look at is a brief overview of light pipe basics and best practices to use in doing light pipe design. We're also going to introduce a few tools that I like to use for efficient light pipe design. These include everything from shape requirements, how to let light escape by using periodic functions, surface features, and textures. Also, I'm going to introduce you to an interactive optimization technique that I like to use for searching for a best result, using lid appearance to check and improve a design before we go to manufacture, so you know that what you're going to manufacture in the end is going to be what you simulated. Finally, we're going to go through a couple of examples, and then we'll have a couple of conclusions that wrap up the whole talk. So, in terms of goals, what is going to be the primary use of the light pipe? And which of the following output goals are most important to you? Is it moving light efficiently around static components, like we've got an LED on a PCB board? We want to then throw the light through the pipe and get it to another location, and then show that uniformly or with as much power as possible if we just want to see a lid on or lid off type appearance. Finally, what's the uniformity of the exit surface going to look like? Is it just going to be power out? Is it going to read an icon? Is it going to show information? That type of goal could be very important to us. And this comes back to efficiency. How much light do we have to get out there? What kind of LED do we want to use? With what kind of power? And from that viewpoint, how is that going to be seen by the user? So we're going to look at lid appearance criteria. Now I'm showing two examples on this page. The one in the top right happens to be a speedometer needle. In this case, what you want to be able to tell is that when that needle moves back and forth on your speedometer, you can read it easily. And at nighttime, when it gets lit up, we can see exactly what mile per hour we're going at, or what kilometer per hour we're going at. And you can see here for this particular system, when we look at the top right image, we can see there's a dead spot right in the middle. And we definitely have that as a problem. Our goal probably on this particular light pipe is to actually have nice uniformity through the whole needle. On the bottom, we have a 3 light pipe system with LEDs at the bottom there, shooting the light up to the top target area. And there's a bunch of different goals we could have for this. One of them is to have no crosstalk. And in this case, we are seeing some crosstalk in that middle pipe going over to the left-hand side. That's probably going to be a problem for us. And that might be one of our goals, to get rid of that crosstalk. So it might be efficiency here. It might be uniformity. It might be how the icons look that are at the end of those particular pipes. So we've got to take that all into consideration when we set our goals. So let's look at basics, what we can do in a light pipe and how light goes from one point to another point. So usually when we're trying to bend light around a particular area, or say we've got a medical construct or some type of other feature that we have to get light around, we're going to use a light pipe. And say we want to do a quick bend. We want to have an LED on one side and we want to have light output on the other side. And we're going to bend it around 90 degrees. One method is to use a 45-degree right angle bend, creating a mirror at that bend, because when we go from plastic to air, light can be TIR'd if we keep below a certain angle to that surface. Usually that's around 42 degrees in the visible. What we see happen here is that if the light is collimated, it's going to bounce off that 45-degree and completely go down to the outer exit surface. Well, that's not what happens in a real LED. About 90% of all LEDs emit in a Lambertian angular pattern, which means they emit plus or minus 90 degrees in both directions, in angular directions, I should say. So we can see that in this light pipe. We can see that light is bouncing around. But notice when we get to that 45-degree surface at the right end, that light exits. And this happens because we're going beyond the critical angle. Light just exits out, and we're losing that light. Now, there's also going to be some Fresnel losses at the entrance and exit port. If the light actually hits that exit port at a greater angle than 45 degrees, we're going to go and TIR back into the pipe, and the light's not going to come out. So in reality, what kind of efficiency did we get from this pipe? Well, it's about 34%. So if someone was trying to say, well, I'm going to have to use a more powerful LED, I'm going to have to pay more money for that LED because I have a poor construct here, we can look for other alternatives. Well, that would possibly be a bending. So we can bend the light pipe less with a larger diameter. In this case, we want a minimum bend radius that is about twice the times the diameter. So what this allows us to do is, instead of going beyond that critical angle and have light exit out of the pipe, we keep it all internally inside the pipe, and we have no losses almost whatsoever. So this is the type of thing you want to look at. We could have used the previous slide's geometry. We had that quick 90 degrees, or we can bend the light slowly around that particular radius, and then the light all stays inside of it. So this does a much better job in terms of efficiency. These are the type of things that you can do in simulation to try out your ideas and hopefully make a better system for yourself in the long run. One of the things that we need to keep in mind when we do all of this designing is to think about étendue. Étendue is a measure of geometrical efficiency. So pretty much geometrical efficiency G, which is our étendue, is equal to pi times S times the sine squared of omega, where in this formula, G is the étendue, S is the area of the source, beam or optic, omega is the half angle of the beam in degrees. If I go to Wikipedia, I get a very nice definition of this. So a consequence of the conservation of étendue is that when an area of a beam is concentrated, the angular distribution of the illumination will spread. So this means if my light pipe goes from a large diameter to a small diameter, the angular distribution that comes out of it will spread. So if I want to, I can make a very collimated type beam coming into this particular light pipe spread by concentrating the diameter of the beam as it goes along. So this is something we're going to use as we go through the designs and the examples that I have in this system, because we want to take advantage of that when we may have a very nice output that we'd like to have, but we want to be seen by a lot of different angles. Say that we're in an automotive application and we have a dashboard, and we have an icon on that dashboard that we want to light up, and we want both the driver and the passenger to see it. So what we're going to want to do here possibly is concentrate that light pipe, so when the light does come out towards the visual aspect of our target, our driver, and our passenger, it gets seen by both of those people. So this is something we can use and keep as an idea using étendue for this type of thing. So what kind of light guide basics can we use to start doing these efficient designs that we've been talking about? Well, light guides typically guide light, and they direct light by total internal reflection usually, because if they're not doing total internal reflection, you've got light leaking out in a lot of different areas, and you may not have very much when you get to your exit surface or where you want to have the light leak out. Common materials for light guides are plastic or glass, and they can be either rigid or flexible. The index of refraction, which is how much light is going to be diverted or refracted in a light guide material, depends on what kind of material we're using. But most of the time for plastics, or even for glass, we're talking about an index of refraction of 1.5, which means our critical angle is going to be about 42 degrees in the visible. What we want to do though is sometimes we want to extract light out, or we want to have it come out quite nicely in a large angular area. Using surface textures is a very nice way to apply a texture to an exit surface to improve both angular efficiency and output. It's all important to have high reflectance on these areas that we want TIR to propagate along the light pipe. Light pipes with poor efficiency, which means that they're very rough in terms of surface texture, allow light to leak out. And I have a lot of people go out and they use a simulation program, and they come back and they say, you know, I'm only getting about a third of the light or a fourth of the light that I simulated in your program. What's going on? I said, well, you know, take that light pipe, put an LED on the end of it, and go into a dark room. Does the whole light pipe sort of emit from all directions? And they always come back and tell me yes. And I say that's because the surface texture on the outside of the pipe is very rough. And being rough, it allows light to leak out. So you're leaking out all of your light before it gets out to the exit surface. And they always come back and say, well, immediately, how do I fix that? And I say, you have to make those surfaces smoother. You need to go to a molder, or you need to specify a better surface texture like an SP1 type finish. And I'll talk about that more in a minute. A diffuse surface is really good for allowing light to exit from an output surface, but it's not so great along those flat surfaces that bring the light along the pipe. So with perfectly flat exit surfaces, we have the same problem we sort of do along the light pipe's outer edges. We want light to leak out, but we want it to leak out where we want it to leak out at. Not along its surfaces where we want the TIR, but around that exit surface, yes, we do. So what we're going to do is we're going to roughen that surface. We're going to add scattering dots or breaks in the light guide surface to force the light out where we want it. And to do that, as we're going along, we want to avoid sharp corners. We want to keep these light guide bend rates as large as possible, and using these gentle bends if possible, and only right angle bends when necessary to maximize light transmittance. And to do that, when we simulate these things, we need to have an accurate source model and surface models so that if the light leaks out, we have that in our simulation. If our source emits plus or minus 90 degrees, we don't use a collimated source, for instance. And to improve efficiency, we're going to put scattering surfaces where they're necessary and where they are on our simulation so it matches what we virtually prototype is what we measure when we create a real prototype. And of course, we've got to trace enough rays in our simulations to make sure that we have accurate answers. Now, in terms of some tips that I can give you, the coupling LED emission into a light pipe has to be good for minimal loss. And we can try indenting the surface, we can try putting power on the surface to maximize LED coupling. We can also consider changing the shape of the light pipe to mix up the light. We can go, for instance, from round to square, round to rectangular, hexagonal, or octagonal. There are all possibilities here using virtual simulation. And this is one of the nice things about simulation. We can try things that we can't do in our prototyping type simulations. In terms of doing trial and error type simulations. To create uniform angular and positional output on the exit surface of a light pipe, you want to have a lit appearance type setup where you want to see in a total hemisphere around that output surface what it's going to look like when you turn on that LED. So we have two ways of doing lit appearance simulations, and I'm going to show you both of those. And we want to make sure that when we do a simulation, that we're letting light escape from that exit surface as much as possible because we want the highest efficiency in most cases. In terms of basics of light guide propagation, light guides, you want to have as much light going out using total internal reflections. And you want to be able to specify that the surface properties that you're using in the simulation are exactly what you're doing when you make the light pipe. So it's very important. Those index refraction is going to be very important for critical angles, so we have to keep track of that. So let's look at some simulations where we can see what really happens inside of a light pipe. Now, if I made a completely smooth, perfect light pipe from my sides here, the light would propagate along. It looks like almost at a 45-degree series of interactions with the sides of the light pipe. And we would get to the exit surface, and it would come out exactly like that. It would come out as a collimated beam. But when we add this roughened surface, you can see that when we get over to that exit surface at the end there, instead of light coming out as a beam, it comes out and it goes out in a Lambertian manner in a plus or minus 90-degree direction. So once again, we're going to get to the end of a light pipe. We want everyone to be able to see this from almost any angle. So we put a rough surface at that end for an indicator like display in an automotive type application or in a medical application or actually in any kind of consumer electronic product where we want anyone to be able to walk up, visually look at this from almost any point and see that it's either turned on or turned off. So we're going to break the TIR by adding a roughened surface. So that's what this particular example shows. Instead of having it come off in one direction with the beam being very tight, where we can only see it very minimally in terms of angular output, that roughened surface does it for us. Well, if you want to send out light in a particular direction, we can add a physical feature. Same type of scenario that we had before. We have this collimated beam coming into the particular light pipe, and we put a feature. This is just a little bit of a notch inside of this particular light pipe. When the light comes up to it, it's going to hit that notch, and it's going to exit out of the surface because of that particular notch. So we're breaking TIR to create and extract some light where we want it. Now, this particular extraction can be done all the way down the pipe, and so we can send out light in both directions. Typically, this is done to try to light up a logo, for instance, that you've indented into the pipe, and this will allow you to have that kind of feature that throws the light out instead of just continues to TIR down the pipe, and we never see that logo. Another type of thing, not everything uses TIR. So for instance, in this hollow light guide, we've put a reflective paint on the interior for a UV type application where we have the light coming in from the top there, that black area. We have light coming in as from a fiber. We put it into the light pipe. Now I have a notch in there. It's a 45 by 45 degree notch. That breaks the light up into a plus or minus 90. Remember, sometimes I say that notch is really good to have. This is one of the reasons for that. It's then sending the light where that notch is, down left, down right, so I have it split and come out the two ends. So this is a very nice non-TIR type application where I use a reflective coating inside the hollow light pipe to send light out in both directions. Let's look at some other things. I'm going to look at 4 different possible scenarios here. And what's going to happen is, should I have the LED inside the light pipe, or should I have it outside the light pipe? So looking at the first particular setup here, I have the round LED against the pipe. So there's going to be a coupling loss. There's going to be Fresnel loss at the beginning of the light pipe, that entrance surface. We're going to need some distance away from the pipe, so I'm going to have light immediately go out and not enter the light pipe. It's going to go out plus or minus 90 degrees. I'm not going to need to tool into the light pipe to make a separate surface, so this can just be a flat surface. And my efficiency is about 76% coming out of it. With the round round LED inside the pipe, there's no loss, especially if it's epoxied into the pipe. And there's no distance required, so I can make this a much shorter distance by putting the LED into the pipe. There is some tooling required, but look at the efficiency, it actually drops down. There's a TIR problem at the end. So in other words, light that hits the back end, if it's flat, is going to total internal reflect off that back surface and come back right to the LED side, that entrance area. So there's a TIR problem. So we're going to have to put a roughness on the end to increase efficiency. That's all that means. Once again, we have a second scenario. This is a flat LED. So in other words, it's a surface mounted type setup. There is no Fresnel loss at the light pipe entrance. There is no distance required because it's right up against it. In this case, we don't need any tooling to help this go out, and our efficiency is around 76%. With the flat LED inside the pipe, using a right side emitting LED here, there's no loss of epoxied into the pipe, so we get an additional 5% on that. There's no distance required. There is some tooling because you're going to have to tool and create a notch for the LED to go into. And our efficiency is about 37%. We have that TIR problem, but once again, we could put that surface texture on the end to fix that. Another thing, how about the shape of the light pipe? We can look at quite a different set of shapes. There's 4 scenarios that we can look at quickly here. We can look at round, rectangular, hexagonal, or octagonal sections. Now, these are just using flat type output on the exit surfaces. For the round, we see that our, in the bottom left-hand corner there, we see an irradiance map and shows the light output is quite uniform. It's round in nature when it comes out, but it's mostly peaked in the middle. And we're going to be able to see that LED as it goes through around this particular bend, and it's going to be much brighter than the edges. In the rectangular type setup, where we have a rectangular output to a rectangular output, we're seeing that the light output gets more of a long line type approach. And it's nice and uniform across the line. But if we do a cross section in the vertical direction, we see that it's not very good in terms of uniformity. And efficiency, it's fine. It's almost as good as our round light pipe, but we're not getting a lot of mixing. Well, with the hexagonal type section, the light goes from one surface side to another surface side and mixes the light up fairly well here. And you can see that in terms of light output. We no longer have that peak. It actually is sending the light out and mixing it so it's more uniform and it comes out in a more uniform manner. The efficiency is about the same, no big problem there, but the light output is now much more uniform on the exit surface. So this is a good way to change the shape and mix up the light a lot better if we're trying to do a bend. Finally, we'll look at an 8-sided type setup with an octagonal type setup, and that mixes up the light pretty well as in this case, I don't think it mixes up the light as well as the hexagonal, but it still does a pretty good job. So there's 4 different shapes and what you can expect when you're using these to bend the light around 90 degrees. Now, there's another thing we need to look at here. What type of LED source should we be looking at? Now, we've got the standard surface-mounted type LED where it emits directly upward if we're putting this onto a PCB board. And that's great if we're going to have the light pipe sit on top of it and we have an exit surface that's roughened at the end to let the light out. This is a perfect type setup, top emitting LED design. What happens if we have a side emitting type setup where we want to put light out where it goes from the left to the right and it comes out that roughen output face we see on the right-hand side there? Well, in this case, in this scenario, we've got 3 LEDs. There's going to be some areas that we want to overlap with the LEDs so we have even uniformity across it. And 3 LEDs work out really well for this type of setup where each of them has a very bright LED type emission in the center, and then they overlap with the second LED, which is next to it, in those areas between the LEDs. So that's this type of scenario here, and the side emitting LED makes it very convenient for light to go out that right-hand side and to create uniformity. So using the LED that fits the type of application can be advantageous. So we keep talking about surface textures. Well, these are the things that let light escape in a large angular area from an exit surface. We know that every surface of a light pipe is imperfect. You can't make it perfect. There has to be, yes, it's great to have a great, nice smoothness using an SP1, but even an SP1 type surface finish will allow light to leak out minimally. If you want to keep light totally internal reflecting inside of a light pipe, make it as smooth as possible. But don't think about painting. When we use a reflective paint on the outside of a long light pipe, there's absorption that goes on. And when you get out to the end, you may have only 10% left if it's a long light pipe. So there's going to be light loss that occurs all the way along the pipe. The best long light pipes that transmit well use a final surface finish that are around an SPI-A1 or A2 smoothness from your molder. So you need to specify to them that because they're going to use their selection if you don't specify it. And how can you test for what kind of surface finish you have? Once again, take it inside of a dark room, turn it on. If you see light leaking out from all over the light pipe, you know that you've got a poor smoothness on that particular light pipe, or you can do a luminance measurement. And once again, if you want to have that large angular dispersion at the exit area of your light pipe, you either have to put that into what you're doing inside of the light pipe as you bring it along, or you have to put a surface texture at the end. So let's take a look at surface finishes. Here's a surface finish guide that I've gotten from Proto Labs. They're an injection molded surface company, and their finish is shown here. Now, if you look at the top of this particular finish guide, the PM-F0 is a non-cosmetic finish. It's a finish that Protomold does to their discretion. You can see that on the left-hand side at the bottom here. That's what that surface finish looks like. And these go all the way from PM-F0 all the way up to SPI-A2, which is shown in the middle figure there. You can see it's nice and shiny. That's done using a grade number 2 diamond buff type setup. And this is a photo that I grabbed off of the Proto Labs website. So you can see some of these different finishes that we're talking about here. The only one that you would probably ever want to use in terms of the sides of a light pipe are that SPI-A2. The output, though, the exit surface, might be any of the PM-T2 or the F0. So how do they create these different types of surface finishes? Well, if we're talking about a A1 type finish, you're talking that they're going to do a grade number 3 diamond buff polish with a 6,000 grit diamond buff afterwards. You can see a very rough surface is down there at the very bottom in the SPI finish D3. That's done with a stone, and then it's done with a dry blast number 24 oxide. So these are the type of finishes that they create, and this is how they do it. This is their guide. Well, there's another way of getting light to start scattering all around, and that's using bulk scatter fillers. These help light diffuse all the way through a light pipe because these little fillers are little scattering surfaces throughout the particular media. As light hits it, it scatters all through the light pipe. This is a cheap method to diffuse light, and it works poorly to mask a direct LED output, but it does make the light bulk scatter all the way through your light pipe. These fillers are typically a whiter colored powder, so you can get a different coloring. If you want, instead of having a clear, say you have a white light pipe, a white LED going through a pipe, you're gonna see white as it comes out. But you can change that color by adding a color powder into the plastic light pipe. Instead of heavy powders, better options are converging and diverging lens surfaces on the entrance and exit port of the light pipe. And sometimes blocking collimation surfaces work as well, especially if you can block the LED output in the middle. That way light has to go around it and you don't get to see the light pipe. Finally, when all else fails, a combination of bulk scatter fillers and surface texturing really help reduce hot spots, where you see a lot of light. Now, these bulk scatter fillers are available from Sept, for instance. You can go to Sept's website at sept-ip.com. You can see a picture down there in the bottom left of these particular fillers, different colors. So now that we've got an idea of what you can do inside of a light pipe, what can we do in terms of virtual prototyping to help you make better light pipes? Well, the first thing that you want to start thinking about is you have an idea and you want to see how good it is. So you want to sketch it in. You then want to put an LED at the end and see how well the light pipe works, see where light's exiting, and be able to visualize what's going on inside of that particular idea. Interactive ray tracing is a great way of doing that. We can visualize where light leaks out, and we can see performance problems while we're designing. TracePro has a 3D interactive optimizer that allows you to do that, to sketch in and then say, these points can actually move during our optimization process. And then you can watch during the optimization process as those points move and what they're doing in terms of your light output from your exit surfaces. And finally, when you get done with a design that you've optimized and looks good to you, you can use photorealistic rendering to discover uniformity issues that might be in there from any target position that you specify, to observe the light pipe from any angle, and to simulate the lit appearance before you go to manufacture to see if you have problem areas. So here's the first of those tools. Here's your surface sketch utility, where you can do interactive optimizing and ray tracing inside of. Now, you'll be doing manual optimization here because you'll be pulling on control points and segment points doing this interactive process. So what you're doing is you grab a hold of a couple of control points, add a few more, add some segments to create this light pipe inside of our interactive sketching capability. And you then specify an LED that has a divergence, and I've put it out to about 55 degrees here. And I want to see how much light's going to come out. Now, you can see that at the bend, you have light leaking out. You always are going to have light leak out because you're going to go beyond the critical angle at some point. But you're trying to maximize how much light you keep in. And we also see from this nice little interactive ray tracing that we have problems at the exit surface. Some of that light TIRs and goes outside as well. So we can start pulling on these control points and these segment points and changing the bend and changing the light to see if we can increase the efficiency and reduce the amount of power being lost. There are nice little CAD tools that are in our interactive sketcher. These allow us to do, for instance, a quick periodic structure on the exit surface to either reduce angular output or increase angular output, depending on what we're trying to do here. In this case, I've put a tricircular type periodic function on the output surface, and I'm able to reduce the angular output because I'm only interested in looking at this light pipe from a front end view straight on. So being able to add some of these very quickly, specifying that the pitch, the central radius, the marginal radius of this periodic function is very simple to do inside the program, and see if this will reduce my in terms of the loss that I have from TIR at that surface, and to reduce the angular output because of étendu. The interactive optimizer that's available allows you to take each one of those control points and segment points that we specified in this particular model, as you see here. I can make those into variables. I can make them into relative variables, so they move a certain amount every single iteration, or that they can move an absolute amount. And then I can specify how much they can move for each iteration. And then as I've set up a merit function in terms of how much uniformity I want, or in terms of how much efficiency that I want, the program will then go off and move those points around, showing me the results for each one of these iterations. So down in the top, in the top left-hand corner, that shows me the error function and what my variables are for each iteration. And down in the bottom right-hand corner there, it's showing me a graph of the irradiance on a target position that I'm looking at. And I can watch this for every single iteration. I can see the system move. I can see the variables move, what those segment points have done in terms of the change. And I can see the results from that particular output for each one of the iterations. So I keep track. If the optimization is not going in the direction that I want, instead of having to wait all the time to come out with a black box answer, I can stop it. I can say, I want to control these points a little bit more, change how that variable moves around in the optimization, and restart the interactive optimizer. Also, after I get done, I can look at each one of these iterations. So I can say, I really liked iteration number 46, but iteration number 32 is going to be a better answer for me because I have a larger angular output and better efficiency, but I didn't get the uniformity I wanted. So I can make a setup, I can stop it there, and maybe change some other parameters, say surface texture or something else like that, and then restart the optimization again. So the interactive optimizer gives me a lot more flexibility if I know what I'm doing. Finally, I talked about photorealistic rendering to create better designs. On the left-hand side of this graph that I'm showing here in the bottom left, this is a photorealistic rendering by TracePro. This is of the initial prototype. This was of a power server handle for Dell. And what happens is that it used to be a black piece of plastic and had no LEDs whatsoever. It never showed any kind of information when it got lit up. What Dell wanted to do was to make this prototype transparent and be able to tell when the power server was working just fine. That was the green light that you see here. If there was a warning going on inside of the power server, to show yellow, and if the power server had turned itself off because of some type of fault, show in red. So this is the initial design, and inside of here, we then took this particular power server handle, we prototyped it. There it is in virtual simulation on the left. There it is using a Ryoko luminance meter, and what was virtually prototyped, was prototyped using trial and error prototyping on the right-hand side. You can see the correlation, they look exactly the same. So if you want to see what the light pipe is going to look like before you build it, virtual prototype it, that's your left-hand simulation result. If you go and build it, that's your measurement on the right-hand side. So you can see there's a very good correlation here. There's a best practice that we can go through here. For that particular light pipe on the Dell, we wanted as high as possible a smoothness, a grade smoothness for high efficiency. So we're going to be talking about an SPI A1 or A2 type grade. At the end of those surfaces, what we found out was to make this simulation better, this is with a smooth light pipe. Well, we're going to want to put different textures on each one of these top and left-hand sides. The texture is going to get to be less smooth as we go from the LED side over to the other side. And so what happens here is we're going to be adding textures, and the textures are going to allow us to have an even illumination. And there's a webinar on the website that shows how this all went down and how we did that in terms of a best practice on that particular design. So we put diffuse surfaces all along that light pipe to send light up. And the roughened surfaces can be everything. They don't have to be just textures. They can be scattering dots on the other hand side, where they work as, when light hits them, as a surface texture to send the light back outward. Or you can put in breaks as well, as I showed you on the light guide that we showed earlier in this webinar. So we can force out the light where needed by using that type of geometry. If you want to know more about webinars, about light pipe basics and principles and some of the things that we've done, there are other examples and webinars on the site. Just go to the TracePro webinars area, And you'll see quite a few webinars on light pipe principles and light pipe basics. Here's the 2 links you can use if you're interested in looking at those. Well, it's about time we go and look at some examples. Okay, we're going to go from a round to square light pipe. And the goals for this particular light pipe is to design a light pipe that uses a round LED and creates a square output at the exit surface to our target. No spot on the target should be twice as bright as any other spot, and we're trying to go from a very small 3 millimeter emitting LED round type system setup to a 25 by 25 for a total of 50 millimeters in a square pattern. The target should easily be seen as being squared, by the way, in that pattern. The lit appearance at the exit surface should be uniform when viewed directly from a forward and from a position to the left 50 millimeters and to the right 50 millimeters. The light pipe should be as efficient as possible using less expensive LEDs if we can. Well, TracePro has this nice little interactive sketcher that I've shown you before. It allows you to specify apertures all along the length of the light pipe. In this case, we'll start with a round aperture on the left-hand side, which is smaller, and a larger aperture on the right-hand side, which is square. So this advanced editor allows us to set these 2 apertures and a path between them. In this case, going and diverging in a nice angular manner. This is what it looks like when we make it in 3D. I've put a LED source which has about a 50-degree emission, so I can make sure that the light pipe will bounce off the sides and it will come out of the exit surface without having to have any texture whatsoever, nice and smooth. Here's a nice initial design. So we see we verified it, looks good. And now we'll go into simulation. So here's the full system. I've got an LED on the back left. I have the round light pipe going to a square light pipe. I put an aperture blocker on it to make sure I've got square output. And then I've got a target where I can see what the uniformity is, and to make sure that I have the capability to see that I've got no more than a 2-to-1 type uniformity on that output target. So on the right is my virtual prototype simulation. I can see an illuminance map. I can see that I'm going from a flux of at plus or minus 25 of around 131 lux to, in the middle there, I dropped down to about 50 lux. But the thing is, I don't really have the square target that I'm looking for, and the edges and the corners, they just don't have my specification that I want in terms of uniformity. So it's a good start, but it's not an answer. Well, I'm going to put a Moltec 11007 texture at the exit surface. So I'm going to roughen it up and see if that helps me out. And sure enough, it helps my uniformity slightly, but once again, I still have a round pattern and I'm not getting the type of efficiency I like. It's still around 23%, but I'd really like to be up at 50% if it's possible, or at least a square pattern. So what I'm going to do is, I said that I could create some type of power on either the entrance surface or the exit surface. In this case, I'm going to want to have it on the entrance surfaces since I want the output surface to be flat. So I've added this converging surface. My efficiency jumped up to 38%, which is a good thing from that 23 initial percent. But the light at the corners falls off quickly, and I'm not getting the efficiency of the square pattern that I want. So I'm going to optimize it. I'm going to throw this into the optimizer, and I'm going to specify that things can change. And look, I've created that rectangular output that I wanted, and I'm getting a pretty good uniformity with no point varying by more than a factor of 2 from any other point. This is an acceptable design since the lux ranges from around 120 to 171 lux, and the efficiency is about 31.8%, so that's really great. I can even remove the blocking aperture. So that's going to make this design cheaper because I did a better job and the optimizer got rid of it and gave me my rectangular pattern that I was looking for. Well, what about the lit appearance though? Well, if I have a very nice smooth light pipe, unfortunately, I'm going to see the LED when I'm directly looking into the light pipe. And that's a problem. A lot of people don't want to see the LED. They want to have it nice and uniform in terms of a lit appearance. Even when I look from the left and right, I'm seeing the light bouncing off the sides on that square, so I get a duplication. So I've got a bright spot in the middle, and I've got bright spots all the way on the sides as well. That's not a very good looking output. And even though it looked fantastic in terms of uniformity, everything else on the target, when I look directly into the light pipe, it doesn't look very good to me. Well, maybe that texturing I always talk about could help. And sure enough, it does. I put that Multec 1107 texture on the exit surface, and look, from the left to right, I've got a very uniform output. Although I'm still seeing somewhat at the center type output, the LEDs, and that could be a problem. It just depends on what I'm trying for in terms of a goal here. I'm not getting the square pattern. That might be a problem. On the other hand, it may be I want to look at a very uniform output on the exit surface target. There I've got it. So it's not perfect, but it's really close. It looks a lot better with the Multec texture. What type of other output alternative design possibilities could we have? Well, we could do a twisted light pipe, and that's what I get here. Unfortunately, that's not going to give me the output that I really want here because I don't get a 2-to-1, and it doesn't really look like a square output, but it might be good for other type of applications I might be interested in. But let's look at using étendue for us. Now, remember I said that if I went from a larger aperture to a smaller aperture, I can increase the angular output. Well, when I do this, and I've created a light pipe like this, I get that square pattern I'm looking for. I get a much nicer lit appearance off of this, although my efficiency drops to 15%. I didn't optimize this particular output, just wanted to show you the possibility of what else was out there. So you can see with a virtual prototyping system, you don't have to go with one possibility. You can try a whole bunch of different ones. Let's look at a second light pipe example. This is a 3-finger light pipe design example that I'm going to be using for an automotive light pipe application. There's going to be 3 icons, T, N, and I. They're going to be the letters T, N, and I. There's going to be dual LED emitters. The icon should be lit up in yellow for normal driving and in red when an emergency situation occurs. No spot on the icon should be twice as bright as any other spot. The icon should be easily read. The icon's lit appearance should be uniform when viewed directly from the forward position. And the light pipe should be efficient with any type of crosstalk between the fingers below 2 orders of magnitude compared to the signal at the exit surface of the icon. So I don't want to see the letter T lit up when the N one should be lit up, in other words. So after I've designed this whole thing, after the design phase and everything else, you can see that T and I that we've created this light pipe for has that bend that we've been talking about. So I'm going to try for a very high efficiency. I want to use a very low intense LED, but I definitely want to be able to see the T, the N, and the I completely lit up. And that's what I get. You can see the output on the target there in the middle, just past the symbols. And if I look at the lit appearance of the T, it's a little bit weak on the outer and left-hand portion, but the middle section is very nice and bright. The system is going to use 6 LEDs, 2 yellow and 2 red for each one of the 3 light pipes, and the T and I symbol is going to be on the dashboard. Well, let's see what we start off with. Well, we use the interactive sketcher, where I create the control points and the segment points for this particular output. And then I ray trace it. I see I get a very good and nice output. We want to move that light vertically up about 1 inch or 25 millimeters. And so that's what this light pipe's doing for us. It's allowing us to do it. We've got a nice slow bend, and we can then push it around other mechanical structure that's in the dashboard. So after we've created that sketch and we've corrected it started off pretty well, we can do a ray trace, and we can look at some crosstalk issues as well. Let's just look at one piece of the pipe. The initial results are quite good. We've got light, it's peaking though in the middle, and it's more, it's falling off slowly as we move away from the center. We do have some crosstalk issues. We have light leaking out of the pipe, but we're getting a very good efficiency. So this is a good place to start. Now, we're going to add icons to the single light pipe, and we're going to check lit appearance with this initial design. So we see that in the initial design, the output's really poor. We're really just seeing a very small portion of the T. This is going to be a problem for us, and we're going to have to do something about using, in this case, we're using a luminance type calculation. We're going to have to figure out some way to get the light to go not only in the middle bar, but on the cross as well. We can try textures to fix the problem, or white bulk scattering paint. Well, in this case, I threw a Multec 11007, which I've done in the past, and I redo the luminance calculation, and we see it worked out quite well in terms of uniformity. We didn't have to add the bulk scattering paint, which is going to drop our efficiency quite a bit. In fact, we have so many nits, we're probably going to want to put a white dense applique on top of this, and that's what's going to make the applique as it goes through to drop the nits down so that it's not so bright. Or we can change to a less bright LED, which will probably save us money. If we trace more rays and we do all 3 of the different symbols, we can see the T, N, and I are actually quite well lit up. I have just traced a few rays. This took a few minutes to do. I could have taken an hour. If I want to do an hour, it's going to fill in the whole pattern and everything else. And I have very nice efficiency here and very fine uniformity. The texture really did work for us, that Multec 11007. But now we need to check the crosstalk in the final design. We said we didn't want to be able to turn on one of the LEDs and then see it in across another symbol. In this case, we're going to turn on the I LED of this particular light pipe. It's going to propagate about 0.05874 lumens through the I symbol to the target. That's going to light it up pretty nicely. This is generally a straight through pass of the sides of the light pipe going through the icon that you can see in this particular ray trace. But we do see that there is some light going from the cross member that holds the three light pipes in place going over to the N. Well, we can see the total amount of power. That total flux of 0.05874 lumens is important because I want to see what it looks like over on the N. So I did these paths. I took a look using the crosstalk capability in the program, and then I went over to the N and said, okay, show me how much power is coming through for the N. It is definitely much, much lower. It's 0.0001, which is almost 3 orders of magnitude lower. It definitely says that our 2 orders of magnitude higher crosstalk path is not there, and we're looking good. So we don't have a crosstalk problem, in other words. So in conclusion, TracePro's interactive optimizers, luminance, photorealistic rendering capabilities provide you the simulation tools that you need to simulate today's light pipe designs before manufacturing, and you can go right from the virtual prototyping process to manufacture after you've gotten a good feeling of how this works. Virtual prototyping is a very efficient model. It's a known process to reduce time and money versus trial and error prototyping. Further, since the computer is doing the work, you can look at multiple solutions instead of just one, and you can investigate those multiple solutions in the same amount of time as you go through that manufacturing process, even if you're doing 3D printing. Because in a lot of cases, you cannot make a 3D printed light pipe that models a lot of things that you can do, especially with curvatures and a lot of the things where you have to start off with a flat surface. Now remember that illuminance and candela maps tell only a partial portion of the story, and you can really get caught with a nasty surprise if you don't do the lit appearance part. So if you have a program and you're using it right now for doing virtual prototyping that does not have the lit appearance capability, you may be missing stuff. So I really think that you might want to consider looking at lit appearance. So I'm now going to put this back to Robin and Dave to help us, and I hope that you've got some questions ready for me.
And thank you very much, Michael. And we do have a few questions here, so let me go right to those questions. And I'd like to remind everybody, if you have a question, now is the time to enter it in the questions box so Michael can respond to you. First question here. Can you just use a polar isocandela plot to see if the output is visible from all angles instead of using an appearance sim?
No, you really can't, because what happens here is that when you do a candela plot, you're collecting the power on a sphere maybe at infinity. And so that's showing you generally where there's light in terms of angular, but it doesn't tell you where it's coming out of the particular light pipe surface. So you may have modes, you may have little small spots that you see at a certain angle, but it doesn't give you how the light is coming off across the whole entire surface. It's just giving you an idea of how the light comes out to a hemisphere outside of that surface.
Okay, thank you. Next question here is, could there be some advantage to an odd number sided light pipe shape?
There's definitely an advantage. As I go back to an idea of when we looked at the cross sections that I showed you, we talked about round, rectangular, octagonal, and in fact, I'm going to go back to the PowerPoint here instead of having you watch every one of these, and we'll go back this way. Okay, as you can see from the slide that I'm showing up now, which is slide number 17, which it doesn't want to show. There we go. You can see that in the round, we had a nice output, but it had a peak in the center. If we wanted to have a better uniformity, the hexagonal shape was a much better answer in this particular design. So yes, having multiple sides is a much better answer. And for instance, if you have a round light pipe and you want to have a square output, that's why the round square example I showed is very valuable, because that's going to allow you to do that.
Okay, thank you. Next question here. Is there a way to change the bend radius instead of segment/control points in the interactive optimizer?
You can add more segments, and in that case, you can then specify a longer length, or you can specify a different radius along different segments. So instead of just having to change a control point, you can also specify that a particular segment is of a different type. It can be straight, it could be a spline, it could be a conic, and you have multiple ways of increasing the flexibility of what that light pipe does by adding more segments and more control points.
Okay, and another question here. Where in the software is the lit appearance function?
There are two places. Thanks for asking that. We have a photorealistic rendering. It's underneath our view menu. And what you do is you set the view up in the system view the way that you want. Then you specify if you want to have an ambient source, or if you want to use the internal sources that you defined in TracePro. And then you specify the exact view in terms of if you want a forward view or a side view. You specify that in the system view using the view set view command. And then you go off and do a photorealistic renderer at one of the 5 different settings: low, medium, high, up to extremely high. Now the second way is there's a luminance calculation / radiance, where there's 3 tabs at the bottom that say system, source, and model, source, and luminance. You go into that luminance tab, and then you specify the view that you want. You specify the number of pixels that you want to then do the evaluation on, and then you go and do a ray trace, which will do both a reverse ray trace backward and do a forward ray trace. The 2 different methods, the photorealistic render is much, much faster. It is an approximation, and so that's underneath the view command, whereas the luminance calculation is an exact ray tracing using the exact colors of the wavelengths that you set up. And each one of these allows you to look at both a linear scale output, a true color scale, and a log scale of that particular event that you're trying to do, either the luminance or the photorealistic rendering.
Okay, thank you, Michael. I have another question here. What efficiency gain would you expect in your first example, switching from 45-degree mirror to bend?
So if we're talking about, I think that with the last type of system that I specified, which was the one that went from a larger diameter to a smaller diameter using the light pipe, I could get up to a 50% efficiency. But what's happening here is a lot of the light is emitting outside of the pipe because I'm trying to get a uniform output in a square pattern where the light's bouncing around and mixing, and it's very difficult to have it go out where I want it with the correct pattern and with the correct efficiency and with the correct lit appearance, because I'm trying to go from Eton is causing me some problems there in getting a higher efficiency. So I'd say about 50% would be the max that you'd probably see, because I definitely need to have a textured surface, and that also has me losing light to my target because it puts it out into a full angular area and just into the target area where I want to square.
Okay, I'm going to ask one more question, Michael, and then we'll wrap things up. This question is, actually, 3D printing doesn't allow us to do pipe design because it doesn't have the polished surface capabilities, and there's a question mark at the end.
Oh, that's correct. Yeah, that's one of the things. If you're trying to get an SP1 type finish out of a 3D printed 3D printed light pipe, you're not going to get it. But what you are going to see is that you should be within a factor of 2 ballpark in terms of efficiency. The angular output should look pretty good, except if you have a lot of exit areas. If you have light where you have like 90-degree bends, the rougher that particular surface is, the more light you're going to have leaking out of the pipe. And it's going to leak all the way along. And if it's a long pipe, you may get very little light out of that end, but you should get the same uniformity. In fact, you should get a very good uniformity if you've got an exit surface texture on that particular light pipe. So really 3D printing can be disastrous, or it can be very close, depending on how what the shape is and how long it is. So, you know, it's a system by system type evaluation, one versus the other. And you can go back and use TracePro to do the 3D printing by saying that the outside surface has a surface texture. If you've measured it and then applying it to the surface, you should have a very, very close correlation between the two. Just change it from a perfect surface finish to whatever you're actually getting with your 3D printing operation.
Okay, thank you very much, Michael. And thank you to all of our attendees for being with us today. And we do have several questions that we haven't gotten to. I just wanted to let people know that I will be sending Michael copies of all of your questions. And we are for those who had a question about a recording, we are recording this webinar, and you will receive a link to the recording in a follow-up note tomorrow. So at this time, I'm going to close the webinar, and I would like to thank Lambda Research Corporation, our presenter Michael Govan, and all of you once again for participating in today's webinar, presented by Lambda Research and hosted by Photonics Media. Thank you.